放在的那怎么样啊？被小偷偷了吗？特别是吧？自己去吧。这个就是中心女生宿舍了。全躺着。
Hello everyone. What is the name of this? Right, so today we will, please take two copies of the handouts. Well, anyway, you all have the handouts in Blackboard. So if you need a bigger copy, you can look at it in Blackboard. Right, so I think we have been going through this course quite fast because we're about to finish. And we still have a lot of lectures left, so which is good. So you have more time to look at other courses. So today's lecture is going to be only of an hour, okay, more or less. And basically today we're going to discuss equilibrium. If you remember, and if I go back to the if I go back to the timetable that okay, so right now we're basically here. Hydrocarbon dew point control, which we will discuss on the next session. And I think after Easter we'll go from to CO2 and H2S removal. So we have gone Nigel has gone through all these sections below, and that will be the only thing remaining from the course. Learning how to design distillation columns and how they work, and CO2 and hydrogen sulfide removal, basically. Right? So today we will start by looking at equilibrium, which is the basis of this design of a distillation column. Okay, so we'll just go through the theory behind equilibrium and what does it mean, and give some examples of binary solutions and how we apply equilibrium in binary solutions. And then next Monday we'll go through next Monday, no? There's no lecture next Monday? Oh, so this is the last one? Yeah. All right. Okay. Then you want to come next Monday? So okay, so then we'll finish distillation columns after Easter in that case, right? So so we'll just look at equilibrium today. So, right, I've received some emails from people, so that will give me time to answer them. So anyway, if next Monday you want to, you have questions, you can perhaps program a meeting with me in my office within the timings of the lecture, right? So send me an email and I'll be able to solve questions for you in case you have them. How do you send the signal? Does anyone know how to send the signal? Oh, hello. I have a problem with the audio visual in my lecture theater. I'm in immersed course L0203. Okay, I'm holding. Thank you very much. Oh, hello. I'm in room L203 of immersed course, and I'm unable to project the screen, the computing screen. No, 203. Yes. Oh, yes, sorry, 202. Yeah? Ah, yes.
Because I saw
Ah, yes, that's it. No worries, thank you very much. Bye-bye. Okay, so the background of this lecture can be found in the Smith Introduction to Chemical Engineering Thermodynamics, which is more the same book that was recommended. We were looking at enthalpy and entropy concepts, second and first law of thermodynamics. Right, so if you look at this system, can you tell me what type of conversion is happening here? Potential to kinetic energy, okay? So what caused the energy conversion to take place? The elevation, yes, the gravity force affecting it there. And what enabled the conversion to take place in a faster way?
Friction.
Well, friction will occur anyway. What? The weight of the person. Well, that's related as well to gravity forces.
potential energy.
The difference on potential energy, well, first of all, that we will be losing potential energy, but basically what is helping this conversion to take place faster is the velocity that is gained through the wheels, right, of the system. So if we were looking at a chemical reaction, right, we will go from one conversion to the other, and whatever will enable the chemical reaction to take place will be the catalyst. And the catalyst, what it's doing is basically what these wheels are doing, accelerating the process and happening the conversion. So we said that potential energy was going to kinetic energy, which is evident for that. Is there any other part of energy where we are also, that is happening in the system? So we discussed a little bit about friction as well. And friction can be with the soil or as well with the air. And friction of the air, how does it dissipate? How does energy dissipate? as heat, as thermal energy. Okay? So really here 2 types of conversion are taking place. We're going from potential energy to kinetic energy and thermal energy as well. Okay, and thermal energy will be basically the losses of the system that are happening, the friction losses of the system, if we want to actually do the conversion from potential to kinetic, right? So normally in a chemical system, for a change to occur, or in order for it to be spontaneous, we always have to lose energy. Okay? So what is happening in the system that we saw previously? The person was losing potential energy. Okay? So therefore, spontaneously, this was converted to kinetic energy. So normally in chemical systems, in order for them to be spontaneous, we need to go from a high energy state to a lower energy state. So normally this is denoted as a decrease in enthalpy. Okay? So we already discussed what enthalpy refers to in terms of energy. What are the units that enthalpy has? What are the units of enthalpy? Joules per kilogram. So energy units, and normally this lost in energy will be sort of a lost, reflected in a chemical system as a lost in enthalpy, right? So therefore, the first thing that it was thought was that originally was thought that enthalpy measured the potential of a system for change. So originally they thought that only the measurement of enthalpy will dictate whether a system will be converted spontaneously to another, or whether the conversion or the energy will not be lost spontaneously. So in this case, if delta H is negative for a process, then the system will occur spontaneously. Okay? So basically, if we were losing energy, if the delta H is negative, and then we have a loss of energy, therefore the system will be spontaneous. That was what it was originally thought. And this basically goes to which law of thermodynamics? First law of thermodynamics. Okay? So normally delta H is defining the first law of thermodynamics, if you remember. Internal energy as well. So it will be equivalent to delta H, the internal energy, if energy is only coming from the system, from the molecules. So what happened later on? Then the second law of thermodynamics appeared. So entropy. So they realized that actually just having enthalpy, a negative enthalpy, didn't dictate that the energy conversion was spontaneous. There were systems where the enthalpy was still negative, but then there was no spontaneous conversion. So that came from evidence from heat engines and chemical reaction, that this was not always the case, and therefore entropy had to be considered. Okay, and what does entropy, for entropy to occur spontaneously, what does it happen in entropy? Okay, temperature will increase entropy, but will entropy decrease or increase in order to be spontaneous? Increase. Okay, so if you remember, entropy is the disorder of molecules. Is basically we tend towards disorder. Okay, so entropy will always tend to increase, while enthalpy will always tend to decrease. So it's completely the opposite. So in order for a system to be spontaneous, it has to have a decrease in enthalpy and an increase in entropy. If both things do not occur, then the system will not be spontaneously occurring. And in order to reflect these two concepts of an increase in entropy and a decrease in enthalpy, then a person, a researcher, professor, don't know, called Gibbs, provided this relationship between these two. And that's where the Gibbs energy started. And the Gibbs energy starter is basically one of the main concepts used in chemical engineering processes. Okay? So basically, the Gibbs free energy relates the enthalpy to the entropy. So somebody occurred to relate these two properties in order to give a new variable that will reflect actually when the process is occurring either spontaneously or not spontaneously. And here we can see that the enthalpy basically has a positive unit because a decrease in enthalpy will dictate spontaneous, and the entropy has a negative unit because an increase in entropy will dictate whether it's spontaneous or not. Okay? And why do we have the temperature multiplying the entropy there? What are the units of entropy?
Joules per kilogram,
Kelvin, okay? So we basically have temperature in there in order to take out the kelvins and have joules per kilogram and have everything in terms of energy units, right? So here Gibbs energy is normally given in joules per kilogram. It's telling us whether something will occur spontaneously or will not occur spontaneously, and it's related to enthalpy and entropy through this relationship.
For what kind of system is applicable? Open system, closed, or both?
Both systems. So any type of system will you will be able to obtain the Gibbs free energy. And it will be applicable for reaction systems, but also for distillation columns. So in any process that you have a phase change, a mass transfer, you always, energy is continuously changing. So we can calculate Gibbs free energy for any type of system, even biological processes, chemical processes, is basically something that is related to.
So according to this logic, all spontaneous reactions are endothermic?
It will depend. It will depend on the system. It will depend because if you say endothermic, so that will mean that you are decreasing the temperature of the system, right?
Do let's say the reactions are like absorbing heat. Is it?
Yes, the reaction could be absorbing heat or could be given heat as well. So the reaction may also be exothermic and occur spontaneously. So for example, if you have two chemicals together, you could have an increase in temperature and giving heat to the system spontaneously through it. So it doesn't have to be exothermic or endothermic. So actually, normally we denote exothermic processes as the ones that have a negative Gibbs free energy, and the ones where you basically occur spontaneously because a negative Gibbs free energy will tell you that the system is occurring spontaneously, okay? So we will have a negative enthalpy plus a positive entropy, then all these will become negative, right? So negative Gibbs free energy, the process is occurring spontaneously. And a positive Gibbs free energy, the process will require energy in order to occur. So I think this is when it comes whether it's endothermic or exothermic. So endothermic is a process where you require energy in order to conduct the system, and exothermic is where the system occurs spontaneously and is providing energy from it. So, so in this case we have the delta G, which basically this will be the change of Gibbs free energy where you have a system where a change is happening, okay? So this will be, initially that's the Gibbs free energy of a solution, of a system by itself. Now, as soon as you have a change, then you convert that Gibbs free energy into a delta G, which is the change of Gibbs free energy, which will be given by the changes in enthalpy and the changes in entropy. So basically here we are just using the same equation but in a system. So for a spontaneous change in the system, gas free energy must decrease. So that's basically the negative value of the gas free energy. And that's consistent with the H decreasing and the entropy increasing. So the gas free energy is used to predict the direction of a chemical process. Okay, so it will basically predict how a chemical process will behave and whether something will spontaneously occur or it wouldn't. You'll need to provide energy. And why this is important in terms of petroleum engineering? Why do you think this will be important?
Energy losses.
We actually do some process separation here.
In process separation, so you will have energy losses as well, and this will be applicable to the systems in there. So this is dictating whether you gain energy or whether you lose energy in the system. Where do you think that the energy lost or gained stops? So is it an infinite process or will it stop somewhere? Equilibrium. Okay, so equilibrium, what we are looking at today, is basically where it dictates where the system will stop. And this is why it's so important, because it's basically telling me where, when we have these changes occurring, when things will naturally stop and where they will settle and not change anymore. So system will tend to change all the time and reach to equilibrium, and knowing this equilibrium will tell you what's actually the point where things are stopping. Okay, so here, for example, we have a chemical system where we have a gas-free energy, and that will be the loss of gas-free energy in order for it to occur spontaneously, right? So here we have over the x-axis something that is called the extent. The extent are general units, just to denote, for example, in terms of a reaction, it will be the moles of the moles that reacted. So that will be number of moles that reacted. Or in a distillation will be the moles that have changed from a vapor phase to a liquid phase. So depending on the type of process, the extent will tell you what actually is happening. So for example, if we have a distillation process occurring where you want to change a compound going from the liquid phase to the from the vapor phase to the liquid phase, then here will be percentage of let's say ethanol propane system, percentage of ethanol going to the liquid phase. Then you will have an increase in the percentage up to equilibrium, okay, where the distillation process will naturally stop because of that. If we have a chemical reaction occurring, then we'll have a number of moles of a product, let's say A plus B equals C, and then C product, then the reaction occurs until you have a percentage of product, and then you have reached equilibrium in the system. Okay? So why is it important? Because this is going to tell you how much product you will get, and this will tell you how much separation you will get. So equilibrium is sort of telling you really where things will yield to, the end result of that. So the gas-free energy will be related to temperature, pressure, and composition. Okay, so all of these variables will affect the gas-free energy. And basically, pressure, temperature, and composition are affecting entropy and enthalpy, as we saw before, right? So we have calculated the entropy and how temperature affects it, how composition affects enthalpy and entropy, and how pressure affects these two systems by the equation. So therefore, they will affect the gas-free energy, right? So, so if we know the delta G, so the delta G will be basically the gas-free energy at the beginning and the gas-free energy at the end, once the system has reached equilibrium, okay? So that will be delta G. So if we know delta G, we actually know what will happen to the system once it has finished? So if we know delta G for a spontaneous change, we will know what will be the end result of that spontaneous change. And this is why it is so important. So what do you think will be delta G over the delta extent? What will be that number? So here we have delta G over delta extent. What will be the end result? The changes in Gibbs free energy over the changes of number of moles. So normally when we have this type of equation, we basically get the equilibrium point, which is reached when that equals to 0. Okay, so which will basically be as well, can be as a derivative so normally in equilibrium you'll basically have the delta G of the equilibrium point will be always equal to 0, and we will soon see this in the temperature pressure chart for a saturation line. So at this point, the energy has reached a minimum energy point. Okay, and this will normally be a local minimum. So let's have a look at this curve, which we also have looked at it when we were looking at entropy, enthalpy, temperature and pressure changes with enthalpy, entropy, you remember. So here we have a phase where we have in the x-axis temperature, Z, pressure, and its free energy. Okay. So then we get this liquid vapor chart, which basically denotes when the system will be as a vapor, when it will be as a liquid, and then in the middle we will have the saturation line. So this type of systems is also, they are similar to systems that we have seen before when we had pressure, temperature, entropy, pressure, temperature, enthalpy, and now we have pressure, temperature, Gibbs free energy, which puts entropy and enthalpy together, right? So what we are going to look at here. So when do you think that this system is basically reaching a chemical equilibrium? Where would you locate the chemical equilibrium in this system? When is the system in equilibrium? Okay. So we have liquid vapor. Okay, so here we have only the vapor. Here we have only the liquid. Right? So normally the saturation line will be the point where we reach equilibrium in this type of systems.
It's like 3.10,
Triple point? No, that's something different, the triple point. I think the triple point is related to more when you have a solid liquid gas phase. in the system. So basically here, the saturation line will be where we reach equilibrium. And that will be important as well for distillation systems. So if we look at this chart, then let's try to make sense. So what happens to the Gibbs free energy as we increase the pressure of the system? It increases. Okay? So as the Gibbs free energy, as the pressure increases of the system, the Gibbs free energy of the system increases. Okay? Is that coherent to, for example, compressing a gas and the molecules move faster?
Why it's increasing Gibbs energy? If you're increasing the pressure,
Yes. If you increase the pressure, the Gibbs free energy of the system will increase. The system will gain energy for this increasing pressure. So for example, if you look at a gas, right, in this chamber, it will have a certain energy. If I compress all this gas in a small chamber, then the molecules of this gas will start moving faster, right? So as they move faster, they have gained Gibbs free energy.
so when the Gibbs energy is zero, it's in equilibrium. Yes.
Yes.
But if it's increasing,
Okay.
The change between
The change of Gibbs free energy. When it's zero, it's in equilibrium. So what happens with the Gibbs free energy with temperature? So what's happening with the Gibbs energy? It decreases, okay? So as we increase the temperature, the Gibbs free energy of the system is decreasing. So it's the same thing as having a vapor. So if we have a liquid and then we transform it to a vapor, the molecules are suddenly expanding, so therefore the Gibbs free energy is smaller.
now in this case, why it's smaller, why that one is bigger?
Because you're compressing the gas. Okay? So basically, as we decrease the temperature, the Gibbs free energy decreases. And as we increase the pressure, the Gibbs free energy increases. And we can see that as well in the equation of G equals H minus Ts. Okay, so you can also see an increase in temperature will decrease the Gibbs free energy because it will make it more negative.
So it will go to the negative side, yeah, Gibbs, for the increasing temperature.
Okay,
excuse me.
so basically, yeah.
You said when we increase pressure, Gibbs free energy is increasing as well,
Increasing.
and then when temperature is increasing,
Mm-hmm.
it's the other way around.
Yes.
But temperature is proportional with pressure. I thought as pressure is increasing,
No. Temperature and pressure are different variables. If you change the pressure, you don't change well, you can change the temperature of certain systems as well, but yes, then it will sort of be non-ideal system where you compress that part and then therefore you increase the temperature of the system, and you'll have to reach a sort of look at the two aspects of that and perhaps end up in the middle of this. Right? So we're looking at them independently. Obviously, if you look at them together, you will be over here, more or less. So you will be in the middle of this chart. So at the moment we're looking at the extremes separately. Yes. So so basically,
So regarding the, if we are in liquid phase, yeah,
yes.
so we are increasing the pressure.
Mhm.
Means we are
Yes,
increasing-
no. The liquid phase, you can have a liquid phase at a small pressure and a small temperature as well. So you don't necessarily need to increase the pressure to have. Both things are affecting the system, pressure and temperature, and will dictate whether your system is in liquid or in vapor, and the type of Gibbs free energy that it will have. It's basically the same thing that we have seen in the charts for entropy and enthalpy. If you put the two charts together, you'll basically get the Gibbs free energy. Okay, so right now we're looking at the two together, basically, in order to derive the Gibbs free energy. And yes, I know that this concept of equilibrium may sound doubting to some of you, but we really don't need to go into the details of calculating equilibrium, of really understanding deep how the equilibrium conditions are reached, because normally this will take a whole course in chemical engineering of distillation columns, of reaction systems, which basically is not the purpose of this. So really what you need to intake is that we have Gibbs free energy that states the energy of a system. The delta G will change and will dictate how the system occurs, whether it's spontaneously and non-spontaneously, and it will stop at equilibrium. And I think if you know that, then we'll have reached certain.
You said when we have a delta G as a minus value, it's spontaneous.
Mm-hmm.
So for the temperature increasing, if delta G is minus, so is this?
Well, this is not delta G. Here we're looking at G alone. We're not looking at delta G.
Compared to the starting point and endpoint.
Okay, if you want to compare starting point to the other one, yes? So then you can calculate delta G and tell whether it's
Increasing temperature.
the compression.
No, so the increasing temperature process is spontaneous.
So an increase in temperature will basically denote a decrease in Gibbs free energy. So depending on what you're starting with, G, what will be the initial G, what will be the final G. So the delta G might not be, I mean, we need to put on numbers really in order to dictate how the system will behave into liquid and vapor spontaneously. But obviously, liquid to vapor doesn't occur spontaneously. It may occur in certain chemicals. Certain compounds may go from the liquid to the vapor spontaneously at a certain pressure, a certain temperature. So it depends what type of chemical we're talking about, what type of compound. I mean, we always say this composition. Here we're not looking at composition. We're looking at pressure, temperature of a system. So, so it will depend on the composition, the pressure, the temperature, how the system will actually be spontaneously, whether as a liquid at room temperature, whether as a gas at room temperature. So that also dictates what you do with certain compounds, right? So if the compound, let's say for hydrogen is a gas at atmospheric temperatures and pressures. So therefore you need to either compress the hydrogen to store it, or to decrease the temperature to liquefy it and be able to have it as a liquid, basically. But if we talk about water, then it's different.
So regarding this one, for example, with pressure distillation, how we use it? For example.
Okay, yes. We'll go step by step. So how we will use this in the distillation column, I will explain in a second. So I think here, so if we stick to what we have said, that delta G in the saturation line, delta G will be equal to 0. So that will mean that in the saturation line, the Gibbs free energy of the liquid will be equal to the Gibbs free energy of the vapor. Okay? And that's basically how we define the equilibrium process. So let's have a look at this example where we have a heating mixture of methanol and water, which is heated to its boiling point. Methanol boils at 64.5 degrees Celsius and water boils at 100 degrees Celsius. So you said, okay, I'll start to heat it at 100 kilowatts. And the initial temperature of this is 25 degrees Celsius. So what do you expect to happen at the boiling point? Once you have reached, well, the first thing you expect to happen is this one to increase the temperature, right? So once you have reached the boiling point, what will happen? Evaporation of what? Okay, so you will expect here to have vapor and only the vapor be methanol.
It's gonna be water.
Why there's going to be water? That's what. Why?
I think it has to do with the molecules. For some molecule of water to evaporate, they need energy. During the temperature to be at 100 degrees, but sometimes some molecules manage to leave the liquid phase and go to the vapor phase with the energy provided. because they have enough energy to the liquid phase.
So remember, we look at mixtures, right? Have we look at mixtures? So we have looked at mixtures, and when we have a mixture, what do? When we have a mixture, we calculate this entropy and enthalpy of the mixture, right? So therefore here we have a mixture of methanol and water. So they're together. So what will be the boiling temperature of this mixture? If we take it like crudely, it will be the average of that, right? As we have more or less done it for the other ones. Or it will be the fraction of ethanol times the temperature and the fraction of water in there. So that will mean that actually we don't have methanol and water separately. So therefore, when you start evaporating this, you won't have only methanol going out of the system. You will have a mixture, as your colleague said, and that mixture will depend on first the temperature that you have reached here, and there the mixture that basically you have in the system. So then you will say, okay, so if I'm still going to have vapor here with methanol and water, then what's the point? How I'm going to separate the system, right? So actually this system that's the way they will behave. Okay? So let's see that we have 0.5 moles of methanol and 0.5 moles of water in the pot. So we're here, 0.5 moles of methanol, 0.5 moles of water. Okay? So then we start heating up, and then after this time we reach the boiling. We start looking at the boiling point of the mixture. Okay? So then we will suddenly produce a vapor and a liquid, right? And this vapor will contain certain water and certain amount of methanol. It won't be the same fraction as what we had in the liquid mixtures. Why? Because we still have methanol, the tendency of methanol to boil faster than the water. So therefore, in the vapor, I will have a methanol water mixture, but methanol will be around, what is the number there? 0.8, right? And then the water will be 0.2, and in the liquid, I will start decreasing the fractions of each one of the, slowly decreasing from 0.5 going downwards. Why? Because the methanol is starting to evaporate a little bit faster in this system. And that's normally, well, this is more or less the average between the two systems, okay? So as we reach the temperature, oiling starts, I have vapor phase with a higher percentage of methanol but still water on it, and therefore I start losing the liquid height. So at that phase, if we have 200 kilomoles of liquids, let's say we have 100 kilomoles of methanol, 100 kilomoles of water, after 280 minutes, which is basically this point in here, what will be the separation that I have reached at that point? The separation that I will have reached will be, I will have in the liquid system 176 kilomoles of liquid consisting of 81.9 kilomoles of methanol and 94.7 kilomoles of water. While in the vapor phase, I will have 23.4 kilomoles of vapor consisting of 18.1 kilomoles of methanol and 5.3 kilomoles of water. And this type of system is basically a system that will reflect a distillation column having only one plate. Okay, so this is a very crude distillation column. And this is something to be considered as well, because, for example, last year we had an oil hydrocarbon system that was coming. We did catalytic cracking of microalgae, and we ended up with, after the catalytic cracking, we basically ended up with a mixture of hydrocarbons, whatever it was formed from the microalgae, with heptane and some water inside that was coming from the microalgae. And we wanted to do the separation. So we say, okay, we want just to take out all of the solvent from the mixture that we have. We didn't know what type of hydrocarbons we had, so we could have very volatile hydrocarbons, but we wanted to characterize that. So then the students say, okay, let's do a distillation, and then we perform a distillation in the lab, and we are able to sort of separate the phases according to the distillation. First we will have heptane, then we will have whatever, and then after we will have the oils. And obviously that didn't happen at all. So the distillation system in the laboratory was basically distilling, so you had an evaporator, but then you had here a mixture. You didn't have each one of the components going on one after the other. So basically, at the end, it became very complicated to characterize the mixture, to characterize what we had in the, what stayed and didn't distill. So therefore, that's why distillation columns exist, because you are unable to perform a whole separation process just by doing one distillation like that. Okay. So now, let's have a look. And this is actually something that we use in the laboratory. In stage 2 chemical engineering laboratories, we do this practical with our students. And in here, what we try to do is basically try to make them plot the equilibrium chart. Okay, so we normally use a lot these equilibrium charts, and these equilibrium charts will basically tell us what will be the mole fraction of two compounds of a binary mixture in the liquid and in the vapor phase. So here we have the same system. We have the methanol water or methanol liquid mixture. And then imagine that we have a condenser, right? So if we have a condenser in this system, we'll basically reach equilibrium. Okay, so everything that evaporates condensates and goes down and goes down. So what would be the most important thing of this system? What would you look in this system if you were heating up through time? What would you be looking for? The temperature at which you reach that equilibrium. Okay? So here, basically, that temperature will be constant throughout the system. So that will be 73.3 degrees Celsius, and then it comes here to the condenser, and then it reaches the system in here, and it goes down. And basically, the condenser, the only thing that it's doing is changing from vapor to liquid, and the other liquid to vapor, and therefore the temperature is not changing in the system, it's remaining constant, and we only have phase changes in the system. Okay, if you remember where we are in the saturation line, enthalpy does not increase or decrease. The temperature does not increase or decrease. It's just enthalpy, what the latent heat, what is happening here. Okay, so in here, what we do in the lab is that we have the distillation column, well, a very small distillation thing, and then we have a heat plate, and then the students start running this type of system, and they record the temperatures. They record the temperatures here and the temperatures here, and the percentage of the mixture. Okay? How do we go? For example, in the lab we have an ethanol water mixture, and then they record the percentage through a technique called refractometry, which tells us more or less the percentage of alcohol that there is in the system. And through that, they basically are able to plot this type of chart. They get the temperature in here, 73, and then they know the mole fraction of the liquid and the mole fraction of the vapor in this system. Okay? And then if we were repeating this system for different mole fractions, then we will have different types of temperature. And we could generate this type of chart. Okay? So this type of chart is basically here liquid, vapor, liquid vapor, liquid vapor, liquid vapor. Okay? And this is for an ideal mixture. Okay? If we don't have an ideal mixture and a binary mixture as well. Okay? So we are looking at a binary ideal mixture, which gives us a very nice chart. If we don't have an ideal mixture binary, then the chart starts behaving not really linearly, starts changing. So what do we have here? This is something that actually in your assignments you were given these equilibrium charts, and this is something that you will need in order to do the distillation column. Okay? So this is telling me for a center temperature, if we reach the saturation line, or basically the equilibrium point, how much of it will be liquid and how much of it will be vapor. Okay? So normally in this type of binary system, and this is normally how the temperature and mole fraction changes. So this is a TXY diagram. So XY denotes binary system, and T is temperature changes against the binary system. So this is the TXY diagram of temperature, mole fraction of methanol, water. So normally you only have the mole fraction of one of the compounds, not of the two, but because you can take the other one by default. Okay? So in this case, we have, for example, at this temperature, we just go to the equilibrium point, and then in here I will have this type of, in the, what is called here is the dew line. And really this type of charts, which you can sometimes find in the literature, most of them were done through experiments, okay, through people observing what's happening and recording this data. So just the way the students are doing it for that that was generated for thousands of binary mixtures, and this is reported, and you can find those charts in the literature. So in this case, we have the liquid, and then when we have the dew point, we basically record the mole fraction, and this is the bubble point. This line is called as the bubble point line. And this is when we have the first sort of bubble. It's really through observation, and that's how they were dated. And then we have the vapor phase in here. So if we want to know the equilibrium of that system at equilibrium, then it will, at a certain temperature, the equilibrium will have this type of fractions.
So
Okay.
reaching this equilibrium, I mean,
Or reaching equilibrium.
yeah, when you reach equilibrium, what will it give you?
It will give you, once you reach equilibrium, what is the fraction of methanol that you will have in the mixture and how much you will have of water. So let's say that we evaporate at 80. Okay? So we want to know that the thing will stop at equilibrium. We have already discussed that things stop at equilibrium. So at equilibrium, you will have this amount of, when you have the separation process occurring, you will have this amount of vapor, and this, in the vapor phase, you will have these small fractions of methanol and whatever's left of water. And in the liquid, what is staying in the liquid and not evaporating will be this amount of methanol and whatever else is water. So you will know what we have already said here. This chart will help you tell how much you have of methanol and water and how much you have of methanol and water in the liquid and in the vapor at equilibrium. And the equilibrium is where the separation is occurring. Is that clear? So here, everything will be liquid. Basically, you will have the methanol water mixture liquid. Here, everything will be vapor, and the middle points will be a mixture between the two of them. Okay? Normally, these type of charts we are looking here at the changes of temperature, and here we assume that we have a constant pressure, which is a correct assumption for distillation columns. Okay, so in distillation columns, we will assume that most of the cases you have atmospheric pressure where you perform the distillation. Although now there are some distillation columns where you can perform the distillation at higher pressures, which helps the distillation somehow, or lower pressures as well. But at the moment, we'll just focus on atmospheric, which is the most conventional case and what is normally used in industry. Okay? So, well, here we have a little bit of what we already discussed, that the liquid and vapor are in equilibrium. The Gibbs free energy of both phases are equal. So I think I've already written that. The Gibbs free energy of the liquid will be equal to the Gibbs free energy of the vapor, and this is the basis for all separation processes that are used in hydrocarbon processing. Okay, especially for those that involve change of phases. So if a liquid and vapor are not in equilibrium, so let's say we have a liquid and we mix with a vapor, then it will spontaneously change until reaching equilibrium. Okay? So if we have two pipelines, one with a gas and one with a liquid, then it will change until equilibrium. If we have the pipeline and we're changing the temperature of the pipeline, and then we have a multi-phase flow as you were looking at with Nigel, then at every temperature, the system will change to the point of equilibrium. Okay, so if you change the temperature, the system will change in moles how many moles will be in the gas, how many moles will be in the liquid at the equilibrium point. And then if you further change the temperature, then the equilibrium point will be different. So therefore your compositions will be different. But it will always change to reach equilibrium. So we have looked at the chart of how temperature changes the composition. Okay? But also pressure can change the composition. I think we'll look at charts like that later on. So, in this case, the spontaneous decrease is achieved by liquid transferring to the vapor and vapor transferring to the liquid in a process called mass transfer. So, yes, again, if we have a multi-phase flow, we can have mass transfer processes occurring in the system, all of them changing the liquid fraction and the vapor fraction at different equilibrium conditions according to how the temperature and pressure are changing in the pipeline of the system, right? So this is very useful because it will tell you in a multi-phase flow basically what type of binary composition you have for a certain pressure and temperature. And let you know if you have a change of pressure through the pipeline, let you know what is the binary composition at the end. Perhaps you had gas at the beginning, but then you change the temperature and pressure at the end, and you end up with a multi-phase flow at the end. So you will be able to know that through this type of equilibrium concept. Okay? Right, so we'll take 5 minutes break, and then I will just go through. I think I have just some slides. Yeah. Fourier equation, okay.
When the partial differentiation is used, so it becomes a part of the component pressure. So what I'm not following is B, its units don't have temperature. So when you differentiate, how do you get?
That's a constant, actually. That's normally a correlation constant provided from the...
But if you differentiate with respect to T, does it not just...
Go?
Yeah. That's what I couldn't... I don't know whether I was just being down. I follow everything about except that. I don't understand why that is.
So this is the differentiation, and then you end up with d over m in here. So I think it will come from differentiated dv, the integral of dv, and then you take out, so you put, so what do you have, yes, so you're multiplying everything times dt. So then you have dv equals r dt pm plus 1 over m dv. So you integrate all of them, and then you have v equals rt pm plus v over m. Yeah, so you multiply
So is that so from that to that? I don't know.
yes, I think this one should be, yes, so I think it's just different ways of expressing the same equation. But basically what you are doing here is you have dv over dt equal r m p. plus 1 over m dv over dt. So if you multiply everything by dt, right, you get dv equals r mp dt plus 1 over m dv.
Oh yeah, I get that. But what I'm to understand is if you differentiate the v with respect to t,
no, you basically, you don't differentiate, you need to take out the differential, and to take out the differential you basically integrate this differential in order to take out all the differentials equations. So in order to solve this problem, the first thing you do is basically you have this delta change in this case, so you want to take out this delta change to be able to differentiate against one variable, to integrate against one variable alone. So you basically take out dt here, and that's where dt appears here. And then with that you're able to integrate and express it this way. And that's why this remains as a constant. I'm not sure.
I'm still not. So do you not start with this and then move to this?
No, I think you have to go. I
Because
think
you use dv dt.
where?
Yeah, so you're substituting this into there.
Yes, but
So I don't understand how you from this, because you only get given this in the formula sheet. Oh yeah.
I think that in here you basically you get first this one, and then you say, well, dv over dt will be equal to that, and then finally you go and you say, okay, so v will be equal to this, and then so you have here b and you have RTP. So you basically solve it, RTP, and then just substitute the volume here. So yes, so basically you say dv over dp dp. dv over dt is expressed by this correlation, right?
Yeah, but what I don't get is, so you're given that, and then you're given v. So then you've got to find out what dv over, like partial dv over dt is. So when you partially differentiate v with respect to t, I don't understand how b over m becomes that. Because if b over m is a constant, it's not just...
No. Well, I think that this was just generalizing the virial equation of state. We're not working out from here to here. So actually in a problem you won't use that. You will use directly this one. This was just a little bit more explanation on how the virial equation of state is generated. So in this case, normally when you have the virial equation of state, you are given normally what are the correlations that and then you use them in the equation by themselves. But this was just coming from the virial equation of state. So here you have this data b over m and 1 over n, and this is for the other one, right? So b over m, then you were given b over m and RTPM, which is here. Yes, it's just repetition really, because we were explaining the concept through an example, but really in the example you wouldn't be given that and then substitute here, no. So this is how this is solved through this. Is the other way around. So I hope it's a little bit clearer. Yes, from that to that. Yes, indeed. So the virial equation of state. So this is normally that's how the viral equation of state appears in the system, and then to solve it you will use this type of system. Okay, yes, I'll make a note just
One question about this.
yes.
So, for example, if I want to have 100% of methanol in liquid phase, do I need to have a temperature of this? Where methanol have mole fraction is 1 for liquid.
So that
So
will
in this
be
temperature, so can I have 100% liquid methanol at the end?
Yes. In this case, you will basically have, but that will be, the thing is that here you have in both systems, so at a temperature of 100, you basically have most of it being the liquid, and a temperature of 71, most of it. So what will tell you is that if the boiling temperature of your system is 73, that's the boiling of methanol. So actually in your binary system you only have methanol, if it boils at that point. If you have methanol water, it will never boil, start boiling at this point. You won't see the first few points at this point. So that will mean that you actually don't have a binary system. You only have methanol in the system.
In liquid, you know, or liquid and vapor.
In liquid and vapor.
I see.
So that will mean that actually you don't have a binary system. And then at 100, that's the boiling point of water. So really, you don't have a binary system. So everything is water, and that's why it's boiling at 100. If you have a binary system, it will never boil at the boiling point of the pure substances. It would boil at a point in the middle. Depending on the mixture.
For your mixture, it doesn't look like this. So I mean, if I want to have a maximum liquid, or if I want to get methanol from mixture,
Yes,
liquid phase,
yes. If you want to get methanol only from the mixture, let's say.
so if I want to have 100% of methanol from the
So
mixture,
you could end up here at this binary
around that point.
where you have, this will be the vapor. In the vapor you will have 96%, and then in the liquid you will have that amount. So you will end up with these two points in the liquid and in the vapor phase.
So in your situation, 100% is impossible.
In pure situations, then you will normally, or you could have a point here and here, but then that will be the boiling point of basically methanol, and that will be the boiling point of water. So you don't have any water, you don't have any methanol, you only have water. So you could start with the mixture. What is the mixture? So we have it in here, and this will start to decrease, let's say, through time slowly, but here you will start having 0, 0, and at some point you will have 0, right? 0 moles of methanol. So at that point, basically, this will start to increase as well, and that will have reached 100. But the problem is that normally you don't reach these points, because you can see how this one is slowly changing. So most of your solution will have gone by the time you reach that point. you will sort of have very little, if not non-solution by the time you reach.
I'm a little bit confusing about this. So you said this is for the ideal mixture point. Actually, this is not mixture point. This is not the binary condition. Because 100%
That's for one.
Yeah, only one.
But if you were removing from here methanol, at some point you won't have methanol in the system, and you could have only end up with water, or with water in the system. So at some point, let's say if this one continues.
But for example, like in this kind of the circulation system, so the either water or methanol cannot escape from this system. So the either in vapor or water, it should be there. This kind of situation cannot happen in this system because water cannot escape from the system.
If you remain at this constant temperature.
Yes.
If you remain at this constant temperature, that's what you are going to have in the system. But if you start increasing the temperature further and further and further, I mean, you could increase it up to 100 degrees Celsius, right? So if you had a very slow increase in temperature, let's say, then it could be that at some, I mean, it's very difficult to reach that, but it could be that you have one drop and that drop boils at 100 degrees Celsius.
So a question, in this kind of system, if you stay with this 73 and you have water in it, and you said that the methanol boiling point is 64, so you will end up with, if you stay with this 73, you will end up with like all the methanol are vapor. Methanol is vapor, and the liquids and water is, I mean, but anyway, you will have, will you have
Yes, I mean,
the droplets?
that's what I think, that this is going to change. The composition will change as you increase the temperature. So as this is constant temperature, right? So this is having this. So this is this point. But then imagine that you were increasing the temperature. So then obviously you will go like that, like that, like that, like that. So suddenly you will end up in here, and then in the liquid you will have basically the smallest amount of methanol. And then when you reach 100, you will have only liquid in here. But in most cases, before you reach 100, most of your solution will have gone by that time.
What do you mean gone?
That water is evaporating all the time. So it will be very unlikely that you reach 100 and you still have water here, pure water in here. It will have gone with all the water that went through all these stages.
But if you stay with this temperature in this closed loop,
Yeah.
so you will end up only with liquid, only water. That's it. The other methanol will be gone. And I mean,
Well, in this
methanol
loop it's always refluxing, so you end up.
methanol will be as a vapor, constant, and all
Vapor is here, and then it comes liquid, but it will always be the same mixture. It will be
but
the
this is
fraction.
closed loop.
This is in the fraction in liquid and the vapor.
This is
In close,
loop.
yes, close loop.
And the methanol purely will gone. I mean, will be as a vapor, but the water will be as a liquid. And this will be 100% water, not mixed with.
It depends. Yes, if you say, well, I want to continue this, I want to start increasing the temperature up to 100. Then the problem is that water is still evaporating in here, right?
But if you're not increasing it,
If you're not increasing to 73, then you will end up with this, and at the end, you will basically have all of it gone with this fraction and nothing in here.
it won't come. It's close.
So all of things will be gone at 0.8. So you will have. In this case, well, this is then you will not. You will have 0.8 of methanol at the equilibrium, and then.
And liquid will be only the water. It won't be methanol.
No, yes, liquid has methanol as well.
Why?
0.5 here, 0.5 liquid, 0.5. Because
It's in closed loop. It shouldn't be like that. Because you all the time, like it's like you this.
yes, but all the time you will have only vapor.
Maintain temperature.
Yes, you will.
But you don't need to maintain it's a 73. And
Yes, but not all of the liquid will go through this stage. I mean, not all of it will evaporate. You will have some liquid staying here, and you will have more water staying here than methanol going up. So therefore, when the methanol and water
So in
mixture
liquid-
reaches here,
in liquid-
you will go down.
In liquid, like what do you contain? Methanol and water or only water?
In a liquid, you will take out the methanol and water together, and here you will have a methanol water as well fraction.
with this fraction.
But this fraction will be higher in terms of water than the fraction in the vapor.
So with 73 you cannot evaporate the methanol. Yeah, whole methanol.
Yes, but if you want to go this one to 90, let's say, anyway the mixture will need to reach 73. So you cannot go from 0 to 90. The mixture will start to heat slowly.
Regarding this graph,
So imagine that they say, no, I don't want 73, I want 100 here, because like that I'll just take out all the water. Or 67, nothing will evaporate because this is a mixture. So basically you will start observing things happening at 73, and if you were applying 100 degrees heating, then it will start heating slowly, so at 73 will still go out.
regarding this graph, so this is only for methanol, yeah?
So if you were having 73 and having the vapor, then at 73 you will get this amount of vapor, right? And then as you increase, then the percentage of methanol will decrease and the percentage of water will increase, okay? And then when you reach 100, then basically you won't have any methanol anymore because most of the methanol will have gone, and you basically have water, and that's why you're able to reach 100. Otherwise you're not able to reach 100 because you have a binary mixture. So here you have a pure component. So basically if you have a solution of methanol and water and you reach 100, you don't have methanol anymore in the system. Yeah, is that all right? Okay, so we'll just continue. I think we'll now take the 2 hours, fortunately. So, right. So let's have a look at these charts, which is basically very similar to what we have seen before. And this is the equilibrium phases. So liquid vapor equilibrium phases, and here we have a binary mixture of ethane and propane. Okay, so we're looking at the equilibrium phase and how it changes against pressure, temperature, and mole fraction. So basically here, what we need to denote is that here we have the mole fraction. In this case, 1 would be the mole fraction of what? So what do you think this mole fraction will be? What type of compound? Ethane or propane? Ethane, why? Why ethane? So why is that? So here is a mole fraction, okay? So we have said that the mole fraction is normally denoted for one compound of the binary mixture. So which compound do you think this mole fraction is denoting? The mole fraction of propane or the mole fraction of ethane? Why? Why the mole fraction of propane? So who said it ethane? It was a guess. Is that how are you going to do things? So, okay, if you look at ethane and propane, can you envisage the molecular structure of ethane and propane? C3? C2? C3? C2, C3. what will be more volatile? T2, okay? So at 300 degrees,
300. So
200 Kelvin,
it,
we have 0 here
it means 0
and 1 up.
should be proper.
So what at 300 Kelvin, what do you think will be higher in terms of volatile? What will go to the vapor surface? Ethane or propane? Ethane, okay? So this is the mole fraction of ethane, right? So at 300 Kelvin, we have 0,
It's you just
would
see
be
from
0 mole
vapor.
fraction propane and ethane, because it's more likely ethane will be more volatile and will basically go higher. So this denotes the mole fraction of ethane, okay? So why will it be the mole fraction of ethane? Because here we have the vapor pressure curve, okay? So basically, ethane will be more volatile than propane, okay? Because it has a C2 structure and propane is a C3 structure. So at 300 Kelvin, it is more likely that you have 1 mole fraction of ethane and 0 mole fractions of propane in this basically curve because of the volatility. Okay, so
Propane will be 0, you see.
propane will be 0 at 300, and then pressure of 0. Propane will be 0 in this case, in the mole fraction. So that will be the mole fraction of ethane, basically, what we're looking in there. And we can see here how that will change in terms of the vapor, the temperature pressure. So here, these two lines that you can see here, basically are the lines that we saw before. So if you take a slice of each one of that, you basically generate the curve that we saw, the liquid vapor region curve. Okay? So if we take a slice of these curves here, pressure, temperature, and mole fraction, we have the liquid vapor region where we have the liquid on the, here the phase of the system will be liquid, here the phase of the system will be vapor, and here we will have a percentage of liquid and vapor, and that is against pressure and mole fraction. And the other one, yes, so against pressure and mole fraction. So here we're looking how the changes of the liquid or vapor system changes according to a change in pressure. Okay. So when we were looking at the chart of mole against temperature, that's a chart that is used in distillation columns. Where do you think you will use this type of chart against pressure? Where would you have pressure changes? In what type of processes? In compressors, in the pipeline. Okay, so normally, for example, in compressors, what we want to avoid is basically having a multi-phase flow. Okay, so in compressors, we don't want to, if we have a compressor, we want to stay in the vapor region, and we don't want to go at all in the liquid region because that will affect the compressor if we start producing liquids in the system. So basically, you will have to ensure that the system is designed in order to not hit the liquid vapor region or change of phase in the system. If you have a pipeline where you have a delta pressure decreasing, then again, you will have to observe, for example, if you want to maintain the pipeline as a liquid flow, then you don't want to go to pressures which are lower that will generate a multi-phase flow and perhaps damage your pump if you have a pump that only has liquids. on them. Okay, so normally these type of pressure systems are useful for compressors and for pipelines, and there are systems where you will have a multi-phase flow. You are using equipment for a multi-phase flow, but you want to know how the multi-phase flow is changing, because the pressure will change and it will affect the binary mixture, and therefore you want to know that, and you can know it through here. So that's why we have these curves of pressure against the mole fraction of a binary mixture. And again, here we're looking at binary mixtures with hydrocarbons. Well, you have a mixture of thousands of components, and sometimes they are more difficult to reflect in that. So this we'll call the PXY diagram. So the changes of pressure, how pressure changes the composition of a binary mixture. Okay, so that's what we call a PXY diagram. The previous one was a TXY diagram, how the temperature affects the composition of a binary mixture as well. Okay, so again here we will have, in this case, that will be the tube line and the bubble line. Which one? Sorry, this will be the bubble line, so that's when the liquid starts producing the first bubble, and that's the dew line when the vapor starts producing the first drop of liquid. Okay? So, and again, this type of system is for an ideal solution, where we have a very nice chart. For non-ideal solutions, we may have things like behaving like that, or I mean charts which really not all of them behave just as nicely as that one.
How to link with this all with the Gibbs energy?
Sorry?
How to link with, because you were saying that Gibbs energy.
So here we're looking at equilibrium. So the Gibbs free energy of the liquid and of the vapor are equal, and the delta G is equal to 0. So right now we're just looking at equilibrium. Remember that Gibbs free energy changes up to the point where we reach equilibrium. So right now we're not looking at changes in Gibbs free energy. We're looking at how we are understanding the equilibrium point, where the Gibbs free energy will reach to, and where things will stop, basically. And that's why we want to know equilibrium, because that's where things stop and we're able to understand them. Is that clear? So here again we're just looking at the TXY diagram, but I think it's just the tridimensional basis. And again we have the liquid vapor region. So we have again the bubble line, and the dew point line, bubble point line and dew point line again. Okay, so this is a little bit just looking at what we already looked before. And here basically is just the pressure temperature diagrams again. So here we're not looking at composition anymore. So we're looking at pressure temperature, and that will tell me, this line is useful because it will tell me when according for a certain pressure and temperature, where compound will change from the vapor to the liquid phase. Okay? But again, that are used to show the ranges over which mixture will boil and condense. I'm not sure if you looked at this with Nigel in the afternoon. So you look at multi-phase flow, right, with him? Did you look at how the composition of the multi-phase flow will change according to pressure temperature? So I wasn't in the afternoon, so perhaps looking at the slides and look at that, but it's basically what I have already mentioned, right? So it's just the fact that multi-phase flow exists and how the multi-phase flow region will change according to pressure and temperature. So what type of multi-flow behaviors can you observe? Do you remember that? Bubble flow, chunk flow, Okay? And what are dependent those flows to? To the velocity of the gas and the velocity of the liquid going through the system, right? So, and also to the fraction of gas and to the fraction, because the velocity is basically the mass flow of gas and the mass flow of liquid. So if you have a mass transfer happening and the masses are changing, therefore you may change from a bubble flow to a dew point flow or to a different flows throughout the pipeline, changing the entire pressure drop, which complicates the whole system. And that's the last slide. And basically, this is just emphasizing what we have already looked at, but in an example. So let's have a look at this example and what it says. So example, a mixture of ethane and propane at 200 kilopascals is heated from 210 kelvins to 230 kelvins, okay? The mixture contains 4 moles of ethane and 6 moles of propane. I don't think you have the example there. So just have a look at the slide. You should have it in Blackboard, but really just focus on this example. So we have a mixture of ethane and propane, so you can use the chart that you had before. It's the same chart, okay? So you don't need a new. Well, 200 kilopascals in this case. So normally these type of plots are when you have a temperature, mole fraction is constant pressure, and when you have a pressure, mole fraction is constant temperature, normally, no? So these plots are normally observed at making constant one. Otherwise, you'll need a 3D chart where we have pressure, temperature, and mole fraction, as we saw before. So the mixture contains 4 moles of ethane and 6 moles of propane. Okay, so we can obtain the mole fraction of ethane just by adding up ethane and propane, 6 plus 4, 10, and moles of ethane, 4 over 10.4. Okay, so that's the mole fraction of ethane. So then we locate ourselves in this chart, and we are mole fraction of ethane here, and then the pressure 200 pascals. So we 200 kilopascals. Okay, sorry, the temperature 210 kelvins, okay? So temperature 210 kelvins and 0.4. So we start here, right? That's where we are. And then it says that the temperature that is heated up is 230 kelvins. So we heat it up to 230 kelvins, and we want to know what are the fractions that we get in the vapor and the liquid. Okay? So then we locate ourselves here, and then we go to the equilibrium points for the vapor and for the liquid, right? So therefore, in the vapor, what will be the mole fraction of ethane? 0.6, and of propane, 0.4. And in the liquid, 0.18 more or less of ethane, and 0.72, 0.82 of propane. So if I were to do this separation heating up at that temperature, that will be the mixtures that I have in the liquid and vapor phase. Okay? So I'll give another example. So let's have a look at this one.
Can we close this glass?
I'm not sure. Is that better?
A bit bigger?
So we have this mixture of 80% of ethane flows through a valve where the pressure is decreased from 1,200 kilopascals to 800 kilopascals. Okay, so the valve decreases the pressure. Find the composition of the liquid and the vapor leaving the valve. So can you do that and tell me the composition? So, right, so we locate ourselves here, right? That's the beginning. And then we have to go to 800 kilopascals. So we come here, okay? And then we just basically find out how much will it be in the liquid, how much will be in the vapor. So again, this will have a certain degree of precision because of these charts, but that's fine. So in the vapor, we will end up with 92. No, I think 0.9 is here, right? So it will be 86. And then here, 0.52. No? 0.52. Right, so here is 54. So as I said, there's a certain degree of precision on this type. So in the liquid, 54% of ethane and 87% of ethane in the liquid. And that's how we know what will be the composition of the vapor and the liquid after the mixture has gone through a valve. Okay? Right, so we'll finish here and then I won't see you in...
For a fully plate displacement, say it's a liquid low fraction, right, for the gas.
Yes, and that's the plate system. Basically that we have.
Okay.
I think that's one of the questions, how many plates you will need in order to achieve the composition that you want. So again, you will have to sort of look at the plates, and that's what we're going to learn on the next lecture in 4 weeks' time, I think.
So we use this information in order to not cross the fitness.
Well, but you don't have to submit immediately, so. And all the information is in Blackboard, so if you want to, you can do it in advance if you want. We have said that for the assignment, you are able to do everything before the destination column. So you should be able to do everything before the destination column, and you should be able to do the destination column if you go and read.
But we cannot count your plates.
Oh yes, that's the only question then. What do you think?
After that, I can apply for the process engineering.
Yes, after that you'll be ready for process engineering.
We can apply for engineering. And I will
You will say.
process engineers.
Yes, yes, yes. Yes, the high. Yes, yes, well, that's what we're going to learn on the April. No?
So what we need to do is the calculation.
Yeah, you do the calculation, everything. Anyway, I put some information on HISIS as well, so you can start reading that part because we only have 2 hours for HISIS. So actually, I think that a little bit of reading will benefit. So you have a lot of time to.
So we said we can do the assignment with this.
With what we
Separation
can,
code.
with the up where we can. Remember,
Do we need this for the code separation?
That's the concept of the distillation column equilibrium, but we haven't looked really at the exact calculations of the number of plates and everything. I mean, everything is in Blackboard, but if you want to wait until we learn it here, then you can do that, but you should be able to calculate everything up to that point. Yeah.
Yeah, if it was renewable, I can understand, but when that oil comes off, therefore we need to go
I'm not in tomorrow, but I'll be in Wednesday or later. Oh, right. Oh, this is good. What's up with it?
You've got the home on, don't you? No, probably 7, 8 cost not.
Oh, TV what? I'll look through, I mean, that's the plus case to go and have a look through TD1 and 8010 and see what else going on. I started on through TD1 and I'll look at the 3 days off on Stephen what's going on. Trying to have a look today and have what's the other one.
Where are you going now?
What's the other one I'm doing this afternoon? I think it's very simple. Not last week, is it?
I've got beef. She actually created some yeah, I actually created this website. Because I'm not a stupid. I did when I went into the office.
Let's at the stress rate to make sure it's the validation.
Why do you have to? Why do you have to? Why is it essential? Because your deadline's in after the exam. Then you have 6 weeks.
Okay. So, you know how many stress cycles are like? So, you know, in operation.
70
1 year.
The only good thing in it.
Okay, so right, so
Definitely. You don't have to go through all the
2 times 3 10% divided by n, and then keep it and then that will give you an answer. But the pressure needs to try and find the stress rate. That's the limit stress rate.
The only thing what I agree with you on the model is the only thing is if you had any problem with it, so the rest of the if you have confidence, then you if you leave it till last minute, then you that's good.